So if you remember from previous session, we were discussing about the null space of a matrix. If there is a linear transformation A which is represented in a matrix form, so then null space of A was this Ax is equal to 0. All those vectors which were taking this A, once this A was applied onto these vectors, so this A was taking all those vectors to 0. That's how we define the null space, if you remember the previous lecture. So all the things were given over here, and then we were saying that if we have to solve this for Ax is equal to B, we will reduce it to what's called as row echelon form, row reduced echelon form, RREF. Okay, and you had some A, you reduced to this. So this is this was the original matrix that we had, suppose, and we got something of this sort. So if you remember, this was your row reduced echelon form. Okay, after that we had two types of things. So you had your pivot columns here, and the rest of the columns were free columns. So then we chose for free variables, we chose 1 0 and 0 1. If it's 2, suppose we have x3 and x4. I suppose x2 and x4 were our free variables. So in the first solution we are giving them 1 and 0, and the second solution we are giving them 0 1, and we are finding the rest of the variables. That's how we were finding the solution. So this was sort of a brief overview of what we did in the previous class. Now if you see, we had left the lecture at rank. What is the rank of the matrix? So if you are given a rank, so we'll have a detailed discussion on the rank I think in next class as well, but today I'll just tell you what a rank in nutshell means. So once you have a matrix, and what you are doing is you have a matrix A as Ax is equal to B or Ax equal to 0, whatever you have this matrix A, suppose. Okay, what you can do is you operate Gaussian elimination on it, you get a row reduced echelon form. So in that, you know that we have two things, we have pivot columns and we have these free columns. You have pivot columns as well as free columns. So the number of pivot columns, so what is this giving you? So this number of pivot columns is basically telling you how many independent columns are there. Independent columns are there. That's what it is roughly telling you. So if you have, suppose if you had in R2, you are taking first and second and third column. So if these vectors belong to R2, you know that one of them is redundant. So you will for sure see that you will only have two pivot columns. So this pivot columns, if you see the number of pivot columns is called as column rank or rank in general. So okay, so if you have a defined rank of a matrix, so what will it tell you? So if you anywhere see, okay, this is a matrix and it has, suppose this matrix is in R3, so 2 4 5 6 4 2 and 6 3 8, something of this. So this belongs to R3 cross 3. So you know each of the vector belongs to R3 here. Okay, now you know that if we have to see the dimension of this, so how many base vectors will be there? You know that the base vectors will be, suppose 1 0 0 0 1 0 0 0 1. Okay, the vectors, the basis vectors will be these vectors. Now what do you mean by these three vectors? Because you at least need these three vectors to span the whole space. If you have to sort of get the whole space and you have to reach all the vectors, so you should have these basis vectors. So now if I am telling you that we have a matrix which is like this, and this matrix is, suppose this belongs to 3 cross 3, this is in the vector in this vector space, and this matrix has rank 3. So what it means is that all these three columns are linearly independent. So if I am saying, okay, so I have column 1, I have column 2 and I have column 3. Now you know that this belongs to, suppose, R cube. So each of the vector, if you see in here, belongs to R cube. Now if I reduced this in row echelon form, row reduced echelon form, and I got something of this sort. So what you got is, you got say one pivot column and second pivot column, and third column was like free variable column. This was your free variable column. So what you can see is like there were only two. This sort of is only spanning R2, because though these two vectors, suppose, were independent and one vector was dependent on these things. So what you can say is now rank is actually 2. So that means number of, suppose you had number of rows. If you have a square matrix, let's see first square matrix. If you have a square matrix n cross n, okay, the maximum rank that can be here is n. Okay, so this is the maximum rank that can be there. So you should have rank less than or equal to this. Why? Because rank actually tells you how much independent information that you have there, whatever vectors you have. So you want to see how many independent vectors are there, and you from that you will see that those will contribute to the number of pivot columns, and those pivot columns will tell you the rank. So I'll stop the discussion of the rank over here, and we will take whatever we have left in the previous session, and we'll come back to the rank. I just wanted to give you what rank means, because I will use this term frequently once I am explaining you this algorithm again. So if you remember in the previous class, we were discussing about this RREF algorithm. So we had a matrix A, and this A matrix was something of this 1 2 3 1 2 4 7 3 and 1 2 4 and 2. This was our matrix that we had. So what we can do is, if you remember the algorithm, so algorithm was written over here. So this was the algorithm. Okay, if you have this A and you have to reduce it to R, because you know that null space of A is equal to null space of R. So you will compute row reduced echelon form of A, then identify the pivot columns, and rest of the columns will be free. So once you identify the pivot column, so you will set this as rank. So this R is number of pivots, this is equal to rank. I just wanted to add this thing over here so that you get the clarity. Why did I sort of discuss the ranks? Then we have this free column. Free column is n minus R. So n minus R over here are free columns, because you will have like these things you can put 1 0 0 and howsoever number of free columns you have. So this thing over here is called as nullity. Okay, so we'll see that we'll have a theorem which is called as Rank-Nullity Theorem. So we'll come to that. I just wanted to introduce you with these two terms. So now what you have is you have this algorithm that we saw. Now A will be reduced to R. So if you operate on this, so what you will get is you will get something of this sort. You will get 1 2 0 minus 2, and then you will get 0 0 1 1, and this is 0 0 0 and 0. This is the row reduced echelon form. I just wanted to give you a different perspective. What you can do is, now the first thing is, if you have to apply this algorithm onto it, you will find the pivot columns. You clearly know what pivot columns are. So pivot columns over here is this, because this is your first pivot and this is your second column's pivot. So these two are the pivot columns. That means your pivot columns are x1 and x3, and these two things were your free columns. So they were your free columns. So you must remember this. So after you get this, you can come with a solution. So, but the important thing that I want to tell you is this. So you have this R now. So what I can do is I'll write this R. Okay. So if you see this R over here, this is the R. So if I just swap these variables, suppose if I swap these variables for time being, I can swap them back later on. So I can do something of this sort. I'll R is equal to, so this is my first pivot column 1 0 0, and I'll bring the second pivot column over here. So 0 1 0. And then I'll shift these two things, this 2 0 0 and minus 2 1 and 0. Okay, so I had initially something of this x1 x2 x3 and x4. So what I did is I swapped these two columns. I swapped it the second column and the third column. If you see over here, I swapped these two columns. So I can swap these two things over here. This can be x3 and this can be x2. Nothing changed in the equation, because whatever change I made in the columns, I accordingly made the change over here. But I have a representation that I wanted to show you. This will make it easy to write it. Suppose this is R now. This is your R. So how I can write this R? This is, if you see this portion, so this is your identity matrix. I can write it as I. This is 2 cross 2. And if you see, these are the free columns. I separated out these free columns. So let's say I can call those as free columns F. And then we have this 0 and 0 over here. Please focus over here. So what I'm telling you is, I just swapped the columns. Now I have this x1, x3, x4 and x2. So you must remember that what I did over here. So now what I did is I had this R. I separated out the identity columns. I separated out these free columns. So if you observe this, what was the solution? So you are giving zeros and ones to the free columns. These you are giving these things. You are giving some values. The free columns were given values 1 0 and 0 1. Then you are getting some solution. You are getting the values for other like pivot variables. But what you had there were pivot variables. So if you see the solution, if you remember, we had this solution. So if I go back, the solution was this: -2 1 0 0. So this column and this was your these were your free variables. And the initial you got -2 and 0, you got 2 and -1. Just remember them: -2 and 0, 2 and -1. If you see, the solution is actually here. The solution lies in this free column. So if I go back, so if you see this thing, so this exactly is the solution, just with the sign changed. Okay. So what I can tell you is that if you want to find a solution, so can I write something of this sort? So the solution basically is this. So you will write this F, but this F will be negative F. Okay. So the F thing, the free columns that you have. So if you see the first original solution, that it had 2 1 0 over here, and then it was suppose 2 1 0 0, something of this sort. It depends, like whatever I have put. I need to remember it for me. So if you see 2 1 0 0, okay, just sign was changed. So there it was 2, now you have -2 over here. So there it was 1, it will be -1. There it was 2, it was -2, it will be 2 over here. If you see, it is exactly like that. So solution is -F. Initially you see here you had 2, you will put -2 over here. Now you have 2 and -1. So if you remember, you had 0 1 over here. Now this thing will be -1, okay, and this thing will be 2. So these were the two things, two solutions that we had. Like this was special solution 1 and special solution 2, and then you do the linear combination to find the whole null space. So I'm just writing it in different representation. This R is there, and you had this I, and you have this F. Now what you can do is, you can see that the solution directly is this IF. So what I can do is, can I write it in such a way so that what I can do is, I'll find this R and I'll find a matrix N, okay, which will give me this 0. So because I was doing AX is equal 0. So I'm trying to tell you, okay, I know that this X they are the vectors, so which will all the combination of vectors or some vectors which will once applied this A onto them, it will land at here. So what I'm trying to tell you is, in this N I can collect all the bases, because you know that null N of A is a null space. It's also a subspace. It's a subspace and it will have basis vectors. So what is basis vectors? Basis vectors are the vectors which will span the whole. If you see what were the basis vectors of this in the particular example, so we had this -2, 1, 0 and 0. This was one basis vector, and then we had 2, 0, -1, 2, 0, -1 and 1. So this was other basis vector. So how was the whole space represented? We said alpha of this plus beta of this. Okay, so if I can collect these two in the matrix, if I can collect both of these solutions in the matrix, so what will I get? I'll get a matrix of this sort: -2, 1, 0, 0, and then 2, 0, -1 and 1. So these two vectors are the basis of the null space. They are basis vectors. Okay, now what I can say is, so this over here, this N matrix, I can write it like this. So R multiplied by N, because for sure I know this is a transformation. If we apply on N onto this, this again will be a matrix, but it will be a matrix of zeros. Let's just do it. So if I take this R, this R was like this, the R was like 1, 2, 0, -2, 0, 0, 1, 1, and then we had 0, 0, 0, 0. So what I can do is I can have this N matrix that I found. The special solutions, I'll just put them in the columns of a matrix. So this is my R, the row reduced echelon form. This is my N matrix. You know what N is. So -2, 1, 0 and 0. So this is 2, 0, -1 and 1. So what you will get is, if you multiply these two things together, you will get 0, 0, 0, 0, 0, 0. Okay, so basically this matrix once applied on this vector, and the same matrix applied on this vector, because you know that both of these are the special solutions of AX, and you know these are the basis of null space. So what I can now call is, I can say this Rn is basically equal to 0. So if I take again, because I told you that the column space remains the same, whatever was the null space of A, null space of R remains equal to null space of A. So what I can tell you, if Rn is equal to A, so this implies directly that An also is equal to 0. If Rn is equal to 0, that means An is equal to 0, because null space is still the same. So this N is null space for both. Do you understand my thing? Whatever I was trying to convince, whatever I was trying to convey to you over here, did you understand? I said, so I will have these solutions. I'll have these solutions, suppose solution 1, solution 2, then I'll put a linear combination of this. That will be my whole null space. But what I can do is, I can represent this null space in a matrix notation, where I'll just collect the bases. So these things can be called as basis vectors of null space. So if you multiply these two things together, if I call this matrix N, if I had this R is a row reduced echelon form. So row reduced echelon form multiplied with this N is equal to 0. But I know that this, if you take this vector and if you multiply it with A, if you see the previous lecture, we have also seen that the A multiplied by this or A multiplied by this, it will land at 0. That means if Rn is equal to 0, because we know that the null space of A and null space of R remain similar. So what I'm saying is, Rn is equal to 0 implies that An is equal to 0. So you can see that we have over here. So you had this Ax is equal to B. So what we had Ax, we just wanted to find one vector. So rather what we did is, we found the whole null space of A, and which was sort of, we took a basis vector. Suppose we had basis 1, basis 2, basis something of this sort. Any questions so far? Okay, why is it important? And let me tell you why is this useful. So before answering this, we had a question that how can we write this Rn is equal to An, because I reiterated multiple times, if you suppose have Ax is equal to 0. So what you do is, you reduce it, you say Rx is equal to 0, you perform the Gaussian elimination. You could have also done the same operation on 0, but 0 will remain 0. Whatever row operations you perform on the right hand side, it will still remain 0. That means null space of A will always remain equal to null space of R. That is why we are able to do this. Okay, so whatever I showed you, this Rn is equal to 0, is An is equal to 0. Why is this important? The first thing is, it gives a compact representation of null space. Now if we have to define a null space, we can say null space of A. How can we define it? Null space of A simply is equal to N and Y. Okay, so where Y belongs to, so you have this R n minus R. Okay, it belongs to those, you had these n columns, and these were your pivot entries. So these are your Y's. Okay, this is how you can define it. And then the second thing is, it helps you solve Ax is equal to B. So if you have to solve Ax is equal to B, so what you can do is, a particular solution xp will exist there, and then ny for y gives you all solutions. So you have xp will be a particular solution first, and then you will have this ny. As I was telling you, suppose you have Ax is equal to 0. So simply, so now if you find one solution over here, if I add B onto this, because I was trying to find Ax is equal to B, so if I add this after that, so I'll get a complete set of solutions. So what I can do is, initially I'll use this concept of null spaces in order to get to this solution Ax is equal to B. Let's take a quick example. Okay, So again, I'll take some examples. So let's say we have a matrix B over here. B matrix is say 1 1 2 2 3 5. This was 1 0 1 and this is 3 4 7. Okay. So now what you can do is we can find the row reduced echelon form. You know how to do that. Okay. So R can be found. So you have to perform row operations and a lot of these things. So I'll get something of this sort: 1 0 0 1 1 1 0 0 0 0 0 0, something of this sort. So this is what I got. So if you see over here, I have told you to what is the way of looking at it. So these things are your pivot columns. So I can write it like this. So this is, I can write it like this. This is my identity and this is my free variable. These are my free variable and this is 0 0. This is 0 0. This is how I can write it also. Okay, what I can now say is pivot column is column number 1 and column number 2. So these are my pivot columns and this column is my like free column or free variables, because I have how many variables? 1 2 and 3 correspond to these things. Now what I can do is, like for the free column, whatever free column we have, we can put one in row 3 and for other 3s we'll get the thing. So what you can get is, you will see n you can get something of this sort. You'll put 1 over here and for rest of the two things you'll solve it. You'll get -1 which we have been doing I think in the previous class we have done this. So this is n that you got. So n it simply had one vector. So anything if you multiply with it with c. So this, if you see this simple vector, this is the basis of n. We can call it basis vector of n. But if you call what is a complete n is this. You multiply it with c and you multiply c with basis vector. So if you have a base vector, suppose something of this a, b, c, d, e and f. These were two basis vectors suppose of null space. Okay. So if you have to represent whole null space, so what you can do is you can take alpha of this plus beta of this. You are taking a whole linear combination. This is your full null space. This is your full null space. And these things are just bases. If you take individually these two things, so these are basis vectors. But when you take linear combination of this, so what it becomes is the full null space. So similarly over here, so this one vector was this n vector. So now if you take this Rn, so if you take Rn, that will be equal to an, that will be equal to 0. Okay, because you had only one vector in this case. So if you even verify this, so take -1 of this, -1 in both the cases. So you see this. So you add these two things together. Okay, if you see -1 it's almost like adding these two things together, but with a minus sign. So it will become -1 0 0, and you add it onto this, so it will become +1 that is 0. So it's satisfied with this for R. If you again take the similar thing, so you add these two things. 1 plus 1 is 2, 2 plus 3 is 5, 1 plus 0 is 1, 3 plus 4 is 7. So you add these two things together and give them a negative sign, and then 2, 5, 1 and 7. So you can add it and you can see it again lands at 0. That means this is pretty valid. Rn is equal to an is equal to 0. Okay, I hope you got the point. So in this case we had to see pivot columns. So in the first case when you saw, so we had two free columns. In the second case we had only one free column, and sometimes we might not have a free column at all. So what will happen that time? If you have, suppose a free column is 1, so if you have one free column, that means your rank is whatever your rank is, that is so rank is suppose you had a number of rows, so that were n, you had this n, and free column suppose were just 1, you will reduce it by 1. So all the other columns will be pivot columns, so that will be the rank. So n minus 1, you will have one free variable, that means you will just have a line. So suppose in this case we had -1 and 1, and you multiplied it with c. So this whole thing was just one vector, one basis vector, and then you had this line which was in the column space. So now if you have two free variables, so what will it give you? It will give you two basis vectors. It will give you 1 2 3, suppose 4 5 6. These were your two basis vectors, and you can take alpha of this, beta of this. So that means you will have n minus 2 pivot variables. Okay, that n minus 2, this also will be rank. Okay, this can also be called as rank because number of pivot is equal to rank. So now you have these two columns over here. So now you have more vectors. But what if you have all the columns are pivot? All the columns are pivot columns. All the columns are pivot column. So what will happen there? That time what you will get is you will get only one vector in the null space of A. Suppose this is a matrix in which all the columns are pivot columns. It's a full rank matrix. What we call as full rank matrix. So what's the meaning of full rank matrix? Full rank matrix basically means no column is dependent on other column. All the columns are independent. So once you have that, that means you will have the nullity will be 0. Basically that means all the columns will be pivot columns. So in that case, null space of A will just have one vector, that is the 0 vector. So you'll have 0 vector in the null space. Whereas it's a full rank matrix. If you remember your lecture on the multiplication, so what I told you that time, if I have a column, if I have a row like this, 1 2 3. Okay, so this is my 3 cross 1. So this is my one column vector. So if I have the matrix of this sort, 4 1 2, this is my 1 cross 3. So if I multiply it, I'll get a full-fledged matrix. That time I told you I'll get a rank 1 matrix, if you remember. Okay, once we were doing matrix multiplication, I told you that what we can do is we can see it in different light. We can take rows and columns, we can take this like column multiplied by row, second column multiplied by column, and we will get full-fledged matrix, but those will be rank 1 matrix. Now you should be able to understand why is this a rank 1 matrix. Why? If you multiply this is 4 times of this. This is suppose 4, 8 and 12. So again this column with this one, this is 1, 2 and 3, and this column again, so this is 2, 4 and 6. So you see all these columns are dependent. So if you reduce it to row reduced echelon form, so what you will get? You will get just rank 1 matrix. So all these one column is only independent. You will get one pivot and rest of these things. So you will get one pivot column over here, one pivot column. If you reduce it to row, because there is only one vector which is independent and other vectors are dependent. So these three vectors are dependent on each other. So if I again remind you that, so we had something of this 1, 2, 3, 4, 5, 6, 7, 8, 9, something of this sort. Minus 1, 2, 3, 4, 0, 1, 6, 1, 8. If we had this, so what I told you is you can look at the matrix multiplication this way. You can take column of this and row of this. So this is 1, 4, 7 and multiply it with minus 1, 2, 3. So you'll get a full-fledged matrix, but this matrix was rank 1 matrix plus. So you'll take this and you'll take this. Okay, this will be 2, 5, 8. Okay, and then you can have this. This is, let's say 8, 8, 0, 1. Something of this. So this again will be a rank 1 matrix. But this is a full matrix. This will be 3 cross 3. This will be a 3 cross 3 matrix. This also will be a 3 cross 3 matrix. Now you got the point. Why is it so? Why will we get rank 1 matrices? Because you know that columns in that will always be dependent. That is, we will be left with only one column which actually has the information. Rest information is redundant. I think we have a question. Yes, please. So now whatever we have studied the algorithm. We have seen what a rank means, what all these things mean. So what we can do is we can code it up. So whenever you have even commands like this RREF and you give a matrix suppose A to this, so you will get an answer out of this. So what I want is I want to get pivot elements. I want to see what's the rank, and I want to basically code this algorithm. So why am I even coding these things up? So that you get into a habit. So whenever you are solving a problem in mathematics and you are solving it on paper, so you should have a habit of converting that thing into a code. Okay, because many of the people, they can do it on paper, but once they are asked to change in the code, it is a headache for them. So that's why this is the right time for you people. So whenever you want to understand something thoroughly, so you can do it on paper, then you can stepwise convert into the code. So we'll do the same thing. Okay. So let me go line by line and I'll show you the code as well. Okay, so algorithm will be something of this sort. So what we can do is, so we will have, we'll convert a matrix into floats initially, and then we'll perform the forward elimination, and then we'll perform the backward elimination. And after that, we'll identify the pivot columns. So let me write it also. I have written it over here. So the first thing is, because it's very important, because the numbers that will be given to me, they might be in some other format, integer, whatever. So, but I want to convert them. So convert the matrix into floats. So whatever entries we have there, so we'll convert that into floats. Once we have them in the floats, then we'll perform the second. We'll perform forward elimination. We'll perform forward elimination, and you know what forward elimination means? Gaussian elimination. That means whatever was below, so we'll make them zeros. Third is perform the backward elimination. Perform backward elimination. So what is backward elimination? So whatever was above these pivots, elimination, make them zero. Okay. After that, once we have these, so we'll have to identify pivot columns. So fourth is identify pivot and free columns. So you will identify these columns. You will identify pivot columns and you will identify free columns. Fifth, you can compute rank, because you have now no pivot columns, so you can compute rank. You can compute the rank. So once you know what the rank is there, you can also compute nullity. So what is nullity? So 6 is nullity. Basically means nullity is, so howsoever your columns were minus the rank, n minus r is called as nullity. Okay. And then the seventh step that you have is we'll build the null space. We'll build the null space. Okay, we'll build the null space basis basic, because we have to build a basis. So build the null space basis by setting each free variable as initially 1, then others to 0, and then solving for the other pivot variables, and then you know the whole of this procedure. I will not write it all the things, so you know what we're going to do. So this algorithm that you see over here, so this will give you what is your row reduced echelon form. We can also find solutions. We can also find null space of it. We can also find rank. We can also find nullity. That's what we want to code. So whatever we have studied from past, say 1 or 2 lectures, so this lecture is sort of summary for that. So we will code an algorithm. If you understood this algorithm, you have understood everything till now. Let's go to Python implementation of this. So we'll use NumPy, because we want to always do the bare bone basics implementation, not relying on the heavy packages. So we'll only use, what we can do is we can directly go to the NumPy and code it. Give me a second or so. Okay, the first thing that I'll do is I'll import NumPy, and before importing, I also want to check that if my environment has NumPy. Yes, it has that. So what I can do is now I'll define a function, a row reduced echelon form with null space. So in that, if you see what I am doing is I'm calling a function. If you see what here, so definition, row reduced echelon form with null space. That is my function's name. Okay, I hope this is visible. Okay, after that, what I can do is I'll get this A. This A will be my matrix, input matrix. Okay, this TOL is called as the tolerance for zero detection. So if you have almost nearly zero entry, so you have this tolerance 10 to the power minus 8. So now what I can do is, as I said, the first step will be to convert all the things to floats, because it might be integers that are given to us. So we'll convert whatever A is given to us, we'll convert them into NumPy, and the data type will be floats. Okay, A is equal to NumPy.array, and you are taking A, and D type is float. You are converting the entries into float. So now you'll get M and N, basically rows and columns. So what I can do is I can get rows and columns. So I'll get this, rows and columns. So if you see M comma N is A dot shape. A dot shape will give me a tuple, and what that tuple will do, so it will sort of unbox into M and N. Okay, so after that I want to create a copy, because I want to also create the reduced echelon form. So for that I will create a copy over here. So if you see, I am writing over here R is equal to A dot copy. So whatever A we have here, create a copy and assign it to R. So once I have that, I'll start from row 0. So initially I'll have row 0, I'll assign this row is equal to 0, and then I'll have also a list of pivot columns, because I also want to keep a track of what are my pivot columns. Okay, so pivot columns basically means wherever I have the non-zero entries, when I am making all the below and above entries 0. This is my pivot column, which will be a list initially. So this is my initialization part. Now what I can do is I can perform forward elimination. I have to perform backward elimination. So what I can do is, for forward elimination, I'll select I'll select a particular column and go in the range of n, and keep on taking this. Suppose I have an entry, I'll make everything below it 0, and we have been seeing that enough times. So what I can do is, so just follow this code. If you have any problems, you can ask me. I can explain it. But I don't think it needs explanation, because we have been doing it since a lot of time. So what I can do is I can find the pivot row. Okay, initially I'll put pivot is equal to none, and I'll say for R in range of row, and absolute value should be given, it should be above tolerance. So you can see over here, so if we have 0, so this is for R in range of, so whatever row currently we are at. So initially we are at row 0, and we will go till row M. Okay, and after that we'll find absolute value of this R comma column, so whatever value there are. So if it is greater than this, then only we'll say pivot is this, other will break. Otherwise, if it is not, so we will say pivot row is none. Okay, we'll break out of this and we'll say pivot row is none and continue. So if it is an entry which is almost equal to 0 or 0 point something, so that's why we have kept tolerance rate is 10 to the power minus 8, because we want to be sure that the entry that we are taking is big enough. Okay, otherwise we want to skip that entry, because that row will not be our pivot row then. So if you see this line of code, so what it is doing is, for columns in range of n, pivot row is initially none. So what we are doing is, so if we are having this R in row, we are starting with 0 initially, and then it will go to towards M, because you know this M is the number of rows you have, total number of rows, and we are taking this entry R and column. If it is above tolerance, if it is say if it is sometimes it might be 0, sometimes it might be 0.00 something. So if it is near to 0, we won't take it. It should be above tolerance, then only we can make it pivot. Otherwise this is not our pivot. So otherwise we'll say that okay, this is not our pivot row and we need to change. And what we can do is, if we didn't if we skipped this, so we will have to swap pivot row with the current row. So what we can do is, whatever current, if pivot row is not equal to suppose row, so whatever row we were at, if suppose we are at 0 row, so if we found that the row that we are at and the pivot entry we found are different, so we have to swap these rows. Okay, so what we can do over here is, so I will take care of the indentation, because I am copy pasting the code, and you will have to be very careful once I am doing it. So this, if you see, if pivot row is not equal to row, I'll swap these. So I am swapping them. Okay, again, if you see over here, so what I am trying to do over here is pivot row is equal to R. So take that row. So if you see this R, so I want to see where is the non-zero entry. So non-zero basically means where this should be greater than tolerance. Okay, so if it is same, if the row number and that is same, then I have no need to swap. Otherwise, if row entry and this pivot row are different, that means I had a 0 initially, and whenever I went down and there I found an entry which is non-zero, I want to swap them. That's what I am doing over here. So R in this is like swapping that row. So we have been doing it, I think, since couple of lectures. So now what I can do is I can scale pivot row to make it 1, because you know how to scale it, because we are doing this row reduced echelon form. Whatever number I have, I can divide it. So I have to scale it to number 1, do that pivot entry, the pivot entry I have. I'll multiply the whole row with that, and I'll divide the whole row with that pivot value. So that whole of the pivot row is divided by that. At least the pivot entry that I have currently will become 1. Okay, then I'll eliminate whatever is below. I'll eliminate all these things, and for the elimination code, you can see what I can do is I can write this. So whatever is below, I'll eliminate that. For or in range of row plus 1 to the M, whatever is below in the columns, I'll remove all those things. So and that's where I'm doing this. So I'm putting r minus 1. This is an elimination step. This is the row operation where it will make sure that the variables below are knocked off. And then what I can say is, if that was the pivot column, I'll append that, because I have also kept a list which is keeping track of this pivot column. So if you see, I am saying pivot columns dot append of column, because right now I had this column acted as pivot column, so I'll append this. Okay, then I'll say row plus 1 and go to the second row again. Go to next row, not just second row, go to the next row. That's what I'm saying. Go to the next row. So if row is greater than m, then you have to break out of the loop. So if you got rows, you got to the end of the row, so you will break out of it. And what is the rank then? I also have to compute rank. I can say, so if I am coming out of this, so I can say rank is equal to length of pivot columns. How so many number of pivot columns were there? That is your rank. Okay, that is what I have done over here. So is there any issue? Okay, I suppose no. This I can write it over here. Okay, so now you can clearly see that till now what I have to do, forward elimination, and I found the number of pivot columns. I also can easily find the rest of the column will be a free column. So what I can do backward elimination. Okay, backward elimination, if I just copy paste, this will be the code for backward elimination. You will have to pause over here and you will have to understand the code, but this is the code for the backward elimination. Okay, so for I in range of rank minus 1 to this, for all these columns, so I'll have to make them 0 above. And what are the free columns? So free columns, the columns which are not in pivot. So I will also identify free columns. So this is my free columns now. So free columns is C, for C in range of n, if C is not in the pivot column. Whatever is not in the pivot columns and they are columns, then it's free column. Then I'll now have to compute null basis. And you know how to compute null basis. I'll have an empty list initially, and then whatever are the free variables, I'll set them as initially 1 and rest the free variables as 0, and then I'll compute the rest of the things. So for free columns in free columns, so this is what I'm doing. So if you see over here, so I'm saying for free columns in free calls, so I'll say x is equal to np0 of n. So if you see, so I'm saying x is equal to np0s of this n, and after that set one free column as free column x free column as 1. So because you are currently at one free column, set that as 1, and rest of them is already zeros. Okay, so once you have that, so what you can do is you can find the solution. You can find this, so and you'll find the value for that. So if I just paste the code over here, you can see. So what I'm saying is, for I in this rank minus 1, I'm trying to basically see, like find those values, special values. Okay, and once I have that, so if you see x pivot column is equal to minus row of some, and you know why minus, because we have seen that I and f. And what I can do now is I can append this x into the null space basis, whatever x I computed. So the x I computed is basically in my null space basis dot append. So I can return this rank. So what I computed over here is, if you see, so I have computed rank, I have computed pivot columns, I have computed free columns, I have computed the null basis. Okay, if I take the whole code and I want to copy paste it, so that with the comments, now you should be able to read it on your own. So I'll remove this whole code which I pasted line by line. So from here I'll paste it all at once. So if you now see, this code is with the comments. Okay, so whatever I told you in the algorithm, that is what is happening. We're initially converting this, then doing forward elimination, and then doing backward elimination. Okay, yeah, we're computing rank here, and then whatever free columns we have, we're putting one free column as 1, rest of them as zeros, and then we're trying to find these x's. X will be our special solutions, and these x's are appended into the null basis, and this is we are computing rank, we are computing pivot columns, we are computing free columns, and we are computing null basis. If you see, all these things are computed over here. Okay, this R is our row reduced echelon form. This is our row reduced echelon form. This is my rank, this is my pivot columns, these are my free columns, and these are my null space basis. Okay, now if I test this, suppose I have an example over here. So I have A1. So A1 is my matrix. So A1 is my matrix that I think we chose. So 1 2 3 1 2 4 7 3 1 2 4 2. Now you see this, if you have this, so what I can do is I can give this A1 as A1 to the algorithm that we just wrote. So it will form a row reduced echelon form. It will give me my rank 1, it will give me pivots, it will give me free column, it will give me null basis. What I can do is I can print all of those. So if I want to print them, so you can see I'll print all of these things. So you see, this is the matrix that we had. This is the row reduced echelon form. Okay, 1 2 0 minus 2 0 0 1 1. I think this is exactly the thing that we did on the paper. Okay, so if some of you remember, this is the exact thing that we got. And rank is 2. Why? Non-pivot entry. The pivot entries over here are the first column and the third column, that is the zeroth and the second index, and the free columns the rest 1 and 3. Null basis, if you see, so now the solutions that we got is these two. Okay, 2 minus 1 0 and 2 0 minus 1 1, and then you take alpha and beta of this, and then these are the null basis. If you want to get null space, you take linear combination of these. Any questions so far? Any questions? Did you understand the whole algorithm? Did you understand the code? So here, whatever we have studied, if you see, this is summary of the things that we have seen. So we had a matrix A, and then we wanted to see Ax is equal, we want to find a null space, and then there was a method by the help of which you want to find a null space, and there we got introduced to concepts like rank, nullity, and all these things. So this algorithm, if you understood it, it means whatever was taught in previous couple of lectures, that you have understood all of that. You have understood how to convert matrix into row echelon form, okay, because in that you will now get pivot entries. That pivot entries will be called as rank, okay, that will be called as rank. If you have length of those, so that will be your rank. So now you also know that how number of columns you have, if you can reduce, if you can remove the pivot columns from them, you will get free columns. And then you have to solve. This is the most important part, where what you do is you solve it for the null basis. So how do you do that? So for the free variables, you will take one entry as 0, rest of the 0, and you will keep on doing it for all the free variables. Okay, give it one value and rest 0. Second time give it give another 1 0 and rest will be give another one value and rest will be given the 0, and then you solve it for other of these pivot variables, and you will get these as null basis. So in this example, if you see, so this was the example that we did on paper also. Okay, the rank is 2 and the column is exactly match the answer that we have given. I'll take any questions if you have.